Everyone, thanks for coming. And today, let's do a review on what we have learned in our week 4 lectures. So first, we learn the definitions of quantifiers. There are two different quantifiers that exist. And this is a mathematical notation. An example would be there exists an integer that is both prime and even. This is true because 2 is such an integer. So there exists means there exists at least one. There could be more. We also have another quantifier called for all, or every element, each, and all. An example would be every natural number is an integer, and this is a mathematical notation. So this applies to all objects in the referred set. In order to prove existential statements, we need to prove that there is one element in the referred set satisfying the statement. There could be more, but as long as there is at least one element, then the statement is true. For proving the universal statement, things are different. Basically, we need to prove that every element in the referred set satisfies the statement so that the universal statement is true. Another thing is to negate for all and there exists statement. So the summary is the negation of there exists x in A such that an assertion about x is for all x in A, the assertion is not true. So we can put the negation sign inside the statement and change the existence symbol to the universal symbol. So the negation of for all x in A, assertion about x is there exists some x in A such that the assertion is not true. So here, a special notice is that for all x, there exists y such that ax, y is true is not equivalent to there exists y such that for all x, ax, y is true. The right-hand side is a stronger statement than the left-hand side because the right-hand side can imply the left-hand side. Next, we discussed what is a combinatorial proof. So it's basically to prove assertion of the form left-hand side equals to right-hand side. So we are finding two different ways to counting numbers. The question is always to ask in how many ways we can count maybe the number of lists or sets. We show the left-hand side is the correct answer, we show the right-hand side is the correct answer, and then we can draw the conclusion that left-hand side equals to the right-hand side. So in our class, the combinatorial proof always involves counting lists, counting sets. We start with the easier side, and we think about how many ways to construct lists or sets under certain conditions. Maybe then we can find a different way for counting. An example would be 2 to the power n minus 1 equals to 1 plus 2 to 2 to the power n minus 1. So this is the number of lists and element list, where each element can only be chosen from 0 to and 1, and the list 0 or 0 is not included. So first, we have zeros in the first n minus 1 position, but we have a 1 in the last position. Then we have 0 in the first n minus 2 position. We have 1 in the n minus 1 position. For the last position, it can be anything, and then we sum up together to get the right hand side. Essentially, they are counting the same thing, so they are equal to each other. Thanks for listening.